In our last episode, I told you about momentum. Momentum is a property that every moving object has. It is calculated by multiplying the mass of the object by its velocity. So there's an equation for momentum, mass times velocity, or we can use symbols. We use a lowercase p or the Greek letter lowercase p for momentum. If either the mass or the velocity changes, then momentum changes accordingly. And we're going to look at momentum changes today and another property that momentum has. Let's take a moment and see if we can connect up what we are learning about momentum with what we learned earlier about forces. Newton's second law says, if no net force is exerted on a system, no acceleration occurs. Does it follow that no change in momentum occurs? Think about that. There's sort of two ways you can answer this question. Both of them, the answer is yes, as long as the mass remains constant. If the mass remains constant in the system, then any change in momentum must be due to a change in velocity. If there's no acceleration, there's no change in velocity. So if velocity is zero, mass times velocity is zero, there is no change in momentum. The other way you could think of it is, in order to change momentum, you need something called an impulse. An impulse is a force applied over time. If you have no acceleration, you have no force, and without a force, you cannot have an impulse. So again, there's no way that momentum could change. So without a net force, there can be no change in momentum. That brings up an interesting question. In an earlier lesson, I was introducing you to the system's point of view, and I had the apple and the orange as part of the same system. And we said that the action and reaction pair, the pull along the rope that the apple supplies, and the reaction pull along the rope backwards from the orange, if you look at both of these as being part of the same system, then that action-reaction pair cancels out and there is no net force. That would mean there's no momentum change, even though this system is moving. So that's kind of a weird thing to think about. Earlier we said if it's in motion, it's got momentum. Now we're saying, well, wait a minute, does it? What we're looking at is not whether or not it has momentum, but is there a change in the momentum due to the motion? So what would happen to the momentum of the system if instead of pulling on the orange, the apple turned around and ran into the orange? What if they collided? That's the sort of question that we want to look at today. Instead of looking at the apple-orange system, I'm going to start by looking at a cannon and cannonball. There's a cannonball inside this cannon, and we are going to look at it as if those two things are part of the same system. If looked at that way, neither one is moving, their velocity is zero, the cannon initially has a momentum of zero. So the momentum of the system before anything happens is zero. It doesn't matter how massive the cannon is or the cannonball. If they're not moving, they have no momentum. Now after firing the cannonball certainly has momentum. And as we saw in an earlier lesson, the cannon also goes backwards. And so it would have some momentum as well. So once you fire the cannonball and the cannon, if we still consider them part of the same system, then you have to now take the mass of each times the velocity of each and add them together to get the total momentum of the system. So the momentum of the system would be the mass of the cannon times the velocity or speed of the cannon plus the mass of the cannonball and its velocity. Now, since this is a one-dimensional problem, we can designate one direction as positive and the other as negative. Traditionally, we look at going towards the right as positive, and so the cannonball has a positive velocity, whereas the cannon, which has the reaction force acting on it, will move towards the left. That will be a negative velocity. Why does that matter? Because when you add the momentum of the cannon and the cannonball together, the cannon's momentum, it's a vector quantity, it's going to be negative. So the negative momentum of the cannon and the positive momentum of the cannonball will actually cancel each other out. If you worked out the numbers, you would find that the net force on the system, when you look at the cannonball and the cannon, even though they're separated as part of the same system, the momentum would still add up to 0, just like it did before the cannonball was shot out of the cannon. Interesting. It was 0 before, and it's 0 after. So if you look at it in terms of forces, the force on the cannonball inside the cannon is equal and opposite to the force causing the cannon to recoil. So the action and the reaction forces are internal to the system, and they don't change the momentum of the cannonball system. Before the firing of the cannonball, the momentum of the system is 0. After the firing, if you add the positive momentum of the ball and the negative momentum of the cannon, then the net momentum is still 0. Net momentum is not gained or lost. It's not that the point that it's 0, it's that it's the same before and after. That's the interesting fact here. So momentum is a vector quantity. It has both a direction and a size or magnitude. Cannonball might gain momentum, but it's at the expense of the cannon. The cannonball system does not gain any momentum by the internal action-reaction force of the firing. So the momenta of the cannonball and the cannon are equal in magnitude but opposite in direction if you actually worked out the numbers. And we will do that in some problems a little later on. Since no net force acts externally on the system, there is no net impulse on the system, and therefore there is no net change in the momentum. Big idea here, the momentum before and the momentum after the action is equal. So whenever we have a system that has a property before and a property after remain the same, we call that a conservation action. So if a quantity in physics does not change, we say it is conserved. If we generalize and extend this particular situation to others, we might find that it's true for all systems, that if the system undergoes a change, but all the forces are internal, there is no net momentum change on the system. The momentum before and the momentum after, if you add everything up, is the same. And so we call that the law of conservation of momentum. There are lots of examples of this, even down on the atomic level. If a nucleus ejects a radioactive particle, the particle goes one direction, the nucleus goes the other direction, just like the cannonball. If two cars collide, if stars explode, it doesn't matter how big or small, the principle of conservation of momentum seems to apply as long as you're looking at a system as being a collection of parts and watching all the internal forces and what they're doing. Now, in the example of the cannon and cannonball, two parts of the system flew apart. Let's consider the opposite situation where two things come together. In other words, we're going to look at collisions. So does the collision of objects also show the conservation of momentum? I hope so. If it does, then the net momentum before a collision, or the total momentum before a collision, should equal the total momentum after the collision. So all you have to do is consider what the objects are, how massive they are, how fast they're going, add them together, and do that before they collide and also after they collide. Maybe they change speed, maybe they change mass, but their momentum should remain the same if the conservation of momentum is true. So momentum can be transferred, can be given from one object to another. Just think of, say, a game of billiards where you have two billiard balls. If you hit one and it hits another, the other can start moving, as shown in this example here. So momentum must be transferred from one billiard ball to the other. How much is transferred? That's the question. Where does this momentum come from? Where does it go? Is momentum created? Is momentum destroyed? That's the question that we're looking at. Now, in the case of billiard balls, the two balls bounced apart. We call that an elastic collision. Technically, what we want to see in the simplified models that you and I will be looking at is something called a perfectly elastic collision. What that means is that the two objects will hit each other, and though they might momentarily go out of shape, they will go back to their original shape after striking each other. There is no friction, there's no heat generated, there's no loss of energy. Then that's a perfectly elastic collision. Obviously, that's an ideal situation. So, if a colliding set of objects bounce apart perfectly, then we call that a perfectly elastic collision. What we'll find is, if we add the momenta of the separate parts of the system together, then it should be the same before and after the elastic collision. So here's a billiard ball, and it's going to strike another. We see the situation that the red ball is moving, the white ball is at rest. If these two collide in an elastic collision, then if it's a perfect collision, what would happen is the red ball would actually come to a stop, transfer all its momentum to the white one, and then the white would move off in the same direction that the red was originally traveling. If both are traveling and they're traveling at each other, then it would depend on their masses and their speeds. What would happen would depend on their masses and the speed. So let's say they had the same masses and the same speed, but in the opposite direction. They could actually collide together and bounce apart. And they would be moving with the speed of the opposite ball. So the red one goes off to the left at the same speed that the white one used to be going. They can also go in the same direction. One can overtake the other. The red one is going faster than the white one. They will eventually collide, and then they will bounce apart. The red one will actually slow down, whereas the white one speeds up to the red's original speed if they had the same mass. Now those are ideal, perfectly elastic collisions, but like I said, that's what we start with when we first start looking at things, rather than involve complications of things like friction and heat. There's another type of collision in which things don't bounce apart, but instead stick together. We call that inelastic collisions. In real life, all collisions are somewhat inelastic because there's always some loss of energy somewhere in the collision. Nothing is perfect like in a perfectly elastic situation, but still we expect momentum to be conserved. Even though the two objects stick together, the total momentum before should equal the total momentum after. The only thing that you have to realize is that in an inelastic collision, the two colliding objects stick together, and so they have a combined motion afterwards and a combined mass afterwards. Now, if they perfectly stick together, there's no broken parts or anything, then that would be a totally inelastic collision, and that's what we are going to assume in our examples. So here's two toy train cars, and the blue one is moving toward the right of the screen at 4 meters per second, whereas the red one is at rest. If this is an inelastic collision, then when the two collide, they will stick together. What do you think will happen? Well, if they weigh the same amount, they should be going half the speed after the collision, right? Because the mass will go up, the speed will have to go down proportionally. So when they hit together and stick together, we expect that speed to be half of the blue car's speed. You could figure that one out just by a little puzzling. But what we want to be able to do is figure it out mathematically in different situations. What if the red car is moving? What if it's going to the left? What if it's going to the right? How do we figure this out? Now, if the two train cars have the same mass, it doesn't really matter what it is. You can make up any number that you want, or I'm just going to keep it as an M, and it will work out just fine. But if one of the cars was moving at 4 meters per second toward the right, then it has a mass and times a speed, it has a momentum. The other has no momentum. You add those two together and you get the net momentum before the collision. Afterwards, they stick together, so they have a combined mass and a combined speed. Well, that combination should multiply and give you the same. Let's find out if it does. So if we take the mass times the speed of the blue car plus the mass times the speed of the red car before the collision, after the collision, it's actually two masses added together. They're stuck together, and there's only one speed. Now remember, the red car was not moving, and so it's whatever mass car you want to use, that's going to be zero momentum. So if we just stick with m as our mass, then we have 4 times m, and on the other side we have 2m times v. If we divide by 2m on both sides to get v by itself, then you see that it is m over 2m, that's 1/2, times 4. That's 2 meters per second, exactly as we predicted. But the point is mathematically, it doesn't matter what the numbers are as long as you plug them into this equation faithfully. You got to make sure that you plug in, that you put the speeds, or not speeds, the velocities in according to their direction. So if they're moving to the right, we'll call that a positive velocity. If it's moving to the left, we're going to call that a negative velocity, and you'll get a negative momentum. So when twice as much mass is moving after the collision as before, then the speed must be 1/2. You can puzzle that out with a proportionality, but even if the speeds and the masses are very different, the mathematics is the same. If we were at school, I'd be having you go to lab right now to work on an air track. This is just a device that has lots of little holes coming out of it, like an air hockey table, and you've got these little sliders on it, and you can make them collide and bounce apart, or collide and stick together. We use a little Velcro and they'll stick together. And so what I'd ask you to do is to make some predictions about what you think the momentum of the system or the speed of the system would be after a collision. Since we're not at school, I'm going to have you simulate this. So let me run through some example problems first. Even though I won't talk about the carts, the math is the same. This is just sort of one of the setups that you might be doing if you're at school. We'd have cart 1 sitting, moving to the right, and cart 2 sitting still, two masses approximately the same. What happens after they collide? Well, we could figure all that out mathematically, carry out the experiment, and then verify whether or not what we predicted would happen actually happens. So instead of these air carts, let me start out, I'll look at two balls here. One's red and one's blue. And we'll say that they're about to collide elastically. So they're going to bounce apart. Let's say that the red one has a mass of 1 kilogram and the blue one is smaller and only has a mass of 0.5 kilograms. Before colliding, the red ball is moving toward the right at 2 meters per second, whereas the blue ball is at rest. It's not moving. Assuming the red ball comes to a stop after the collision, how fast and in which direction is the blue ball moving after the collision? Well, to solve one of these problems, first of all, you have to recognize it as a collision problem, and therefore it's probably going to be a conservation of momentum question. You can figure out, if you assume conservation of momentum, that the momentum before and the momentum after should be the same. That means the components of the momentum before and after should be, if you know enough of them, you should be able to figure out the ones that you don't know. So if we say that the momentum before is the mass of the red ball times this speed, plus the mass of the blue ball times this speed, and the same afterwards, but there's going to be different speeds, the masses will be the same, and we can figure this out. So basically, as you read through a problem, I've tried to tell you before, the best thing to do is slow down and write everything down. In this case, you got a lot to write down. You want to know some masses, some speeds before and after. But if you read through the problem, they're all lined up for you. So we have the red ball has a mass of 1 kilogram. The blue one has a mass of 0.5 kilogram. Before collision, the red ball is moving at 2 meters per second. The blue ball is at rest. That means 0, or 0 meters per second. Now, their masses are going to be the same afterwards. And so you might as well just go ahead and write that down again, 1 kilogram and 0.5 kilograms. It says that assuming the red ball comes to a stop after the collision, what does that mean? It means the speed afterwards is 0. How fast and in which direction is the blue ball moving? So our question, our unknown, is this velocity afterwards. That'll be speed and direction of the blue ball. We can set this up as a conservation of momentum question like this, and then just start plugging in values. The red ball had a mass of 1 kilogram and is moving at 2 meters per second. The blue one is 0.5 kilograms and it was not moving. Afterwards, the red ball still has 1 kilogram mass, but it's not moving. The blue one still has a 0.5 kilogram mass, and we don't know how fast it's moving. You can probably see that the 0.5 kilograms times 0 is going to be 0, and the 1 kilogram times 0 is going to be 0. So we're going to simplify. And now we're going to divide both sides by 0.5 kilograms. So 2 kilograms divided by 0.5 will be 4. And the kilograms cancel out, the meters per second do not. So it's 4 meters per second. You'll notice it's positive. That means the blue ball is moving at 4 meters per second toward the right side of the screen, the same direction as the red ball. It's going twice as fast as the red ball. And when you think about it, that makes sense because it was twice as small. So that's an elastic collision. Let's look at an inelastic example. Instead of balls, I'm going to use these little train cars here. Let's say that the two toy cars are about to have an inelastic collision, and let's use the same numbers as before. So the pink car has a mass of 1 kilogram moving at 2 meters per second toward the right. The yellow car has a mass of 0.5 kilograms, but it's at rest. Now you might say, well, it's the same numbers, you're going to get the same answer. Oh no, this time they don't bounce apart. After the collision, the two cars are stuck together. This is an inelastic collision. So how fast and in which direction will the car combination move is the question that we're asking here. So even though this is an inelastic collision, we still expect that the conservation of momentum principle applies, and we can set the equation up basically the same. It's just that the right side of the equation will look a little different because after the collision, there's only one mass. It's a combination of two cars, and there's only one velocity. Okay, they're stuck together, so they're both going the same speed and direction. So we can set the equation up in an inelastic collision to look something like this. So the mass of the pink car times its speed before, the mass of the yellow car times its speed before. If you add those two together, that's the total or net momentum before the collision. That should equal the net momentum after the collision. Instead of saying pink plus yellow, I'm going to call that the system. So the mass of the system times the speed or velocity of the system afterwards. So again, we have our list of variables, and we just read through the problem and set them up. So we've got a 1 kilogram pink car going at 2 meters per second, a 0.5 kilogram yellow car that's not moving. Afterwards, what is the mass of the system? Well, you add the two cars together. So it's 1 kilogram plus 0.5 kilograms equals 1.5. So the total when they're stuck together is going to be 1.5. The question is, what will be their speed and direction? If we apply our conservation of momentum equation to the question, then to plug in the numbers, you see that 1 kilogram times 2 meters per second plus 0.5 times 0, that's going to be 0, equals 1.5 kilograms times the speed of the whole system. So 2 kilogram meter per second plus 0 equals 1.5 kilograms times the speed. Divide both sides by 1.5 kilograms. Kilograms cancel out. You got 2 divided by 1.5, and that's approximately 1.3. I'm not going to put more significant figures in there since we're really rounding off the numbers here. So you do have to watch for that there is going to be some rounding error. But what we're saying is the speed of the system is 1.3. Now remember, that's positive. That means it's going towards the right of the screen. So the two cars stuck together should move 1.3 meters per second, slower than the pink car originally was going. And that just makes sense. Since it's now heavier, it should go slower. So it's going to move at 1.3 meters per second toward the right side of the screen. Let's do one more example. We'll have the same setup, but this time, instead of letting the yellow car be at rest, let's let it be moving. In fact, let's make it move pretty fast. So this time the yellow car has a mass of 0.5 kilogram and is moving to the left at 8 meters per second. So after the collision, the two cars are stuck together. How fast and in which direction will the car combination move? So it's going to be the same setup as before. We still think the conservation of momentum applies. The equations look very similar to what it did before. All we have to do is find out what those numbers are, those values are. So if we make our list, again, it's 1 kilogram going at 2 meters per second, 0.5 kilograms, but this time it's going at 8 meters per second. But notice, we said it's moving toward the left side of the screen. That means it's a minus 8 meters per second. That makes a big difference. Afterwards, it's still stuck together, so it's 1.5 kilogram, and the question is, how fast and in what direction will the system move? If we set it up just like we did before and plug in our numbers, this time the 0.5 kilograms does not cancel to 0 because it's 0.5 times minus 8 meters per second. So we got 2 kilogram meter per second plus a negative 4 kilogram meter per second equals 1.5 kilograms times the speed or velocity of the system. 2 plus a negative 4 adds up to a negative 2. And you got to keep up with that. That makes a difference. If we divide both sides by 1.5 kilograms, then we get a negative 1.3 meters per second this time. That means the stuck together cars are moving toward the left. They're going in the same direction as the yellow car was originally going because the yellow car had more momentum to start with, and so it knocks the system toward the left. So that's basically how you do conservation of momentum questions. What I want you to do now is to try your hand at some simulated collisions, and there's a separate video showing you the directions for that lab, but I'd like for you to do this lab and get it finished, and if you need help, please send me a message. Don't sit there and struggle with it. But it's basically the same setup as we have here. The question is just slightly different. The question I'm asking you in the lab is the conservation of momentum true for the simulations? Is it the same net momentum before and after the collision? But if you need any help, please, please, please contact Dr. Kemp.